So in order to start, let me start by recalling what happens for the Laplacian, because after all, we're going to sort of mimicking. I mean, it's not really mimicking, but the idea is more or less to create a similar problem for the Bilaplacian. So in the case of the Laplacian, whenever you consider an equation like minus delta u equal f, the two main boundary conditions that one may think of are Dirichlet and Neumann. So physically speaking, if you consider this problem as the model of a membrane where F is a load put on the membrane, F in L2 or H minus 1, so this, the unknown U represents the displacement of the membrane from the position at rest. So in the Dirichlet case, where you set U equals 0 at the boundary, the membrane is framed, while in the Neumann case, you have a free membrane. So this condition is sort of a natural one. And in the middle between a framed and a free membrane, there is an elastically supported one, which is given by the famous Robin problem. So here the equation stays the same. The boundary condition you see is sort of an interpolation between the two. And this beta is a parameter that is actually, in general, is a function defined on the boundary of omega, and it represents the elastic response at the boundary. So whenever the membrane displaces from the boundary, this is an elastic response. So this is the problem when you have a load on the membrane. Since in this talk we will mainly consider eigenvalues, let me restate all these problems in the eigenvalue form. You see that the problems are the same. You just replace f by lambda u, and in this case, lambda is the frequency of the membrane. So in this case, the membrane is still framed. In this case, the Neumann case, the membrane is still free, while in the Robin case, the membrane is elastically supported. Now, the quadratic form or quadratic forms associated with these problems are all more or less this form here. So in the Dirichlet case, the problem is set in H10, so this term actually disappears. You don't care about this. In the Neumann case, you see that it's just a special case of the Robin problem where beta is identically 0. So this term again disappears. While in the general Robin setting, you have this form set in H1. Again, beta could be a function defined on the boundary. In the rest of the talk, we will mainly consider, actually, we will only consider the case of constants. So keep in mind that it could be a function, but for the sake of simplicity also, we will consider constants. So let me state some quite known facts about the relation between Dirichlet, Neumann, and Robin problem. So, as we said, when beta is identically 0, the Robin problem is actually the Neumann problem. When beta goes to plus infinity, the Robin problem converges to the Dirichlet. So you see that here, essentially, when beta goes to plus infinity, it's like saying that if you divide by beta the boundary condition, this is actually saying that u is equal to something that is going to 0. And it's a little more complicated than this, but more or less this is the idea. So when beta goes to plus infinity, you recover the Dirichlet problem. There is convergence of the eigenvalues and of the eigenfunctions. And if the domain is smooth, there are also rates of the rates of convergence for the eigenvalues are actually known. The interesting case is when beta is equal to 0. Now, when you consider elastically supported plates, the beta negative doesn't make much sense, but mathematically it actually makes a lot of sense to consider the case for beta negative. And what happens is that the eigenvalues go negative. You have the appearance of negative eigenvalues, while for beta positive, all these problems say you know that the Neumann problem has just a single eigenvalue equals 0, where the eigenspace is given by the constants. The Dirichlet problem has spectrum strictly positive, while the Robin problem has a strictly positive spectrum when beta is positive, but when beta is negative, actually you have the appearance of negative eigenvalues. And the interesting fact is that when beta goes to minus infinity, we actually know that any eigenvalue diverges as minus beta squared. And this, by this I mean that if you fix k, natural number, lambda k goes to minus infinity, which is different than saying that all the spectrum goes to minus infinity, because in fact, there are branches, analytic branches of eigenvalues that stay positive. And the interesting fact is that they accumulate at the Dirichlet spectrum. And another interesting fact is that of shape optimization for the eigenvalues. So the question is, you want to optimize, say, maximize or minimize the eigenvalue lambda k of omega, where you set some constraint on omega, for instance, say the volume, you fix the volume. And it's known that when beta is strictly positive, the first eigenvalue of the ball is the smallest. And we have recent results about also quantitative estimates in this sense. When beta is equal to 0, lambda 1 is 0, so it's not really interesting. But when beta is negative, the interesting thing is that apparently the ball stays it stays the optimizer for beta very small, but then when beta started getting big and big, negative, then the ball is not the optimizer anymore. So these are more or less the facts that we are going to analyze in the case of the Bilaplacian. And another interesting thing is the relation between the Robin problem with the Steklov problem for the Laplacian. So just to recall, the Steklov eigenvalue problem for the Laplacian is this, in a sense, different, strange problem with respect to the others, where the eigenvalue is on the boundary, not anymore in the interior of omega. So eigenfunctions, Steklov eigenfunctions are actually harmonic function, and there is this equality going on in the boundary. So the interesting thing is that there is a sort of a strange link. I'm not an expert in this kind of relations, but some of these properties of this link are used, for instance, when analyzing the Dirichlet-Neumann maps. There are problems that are related both with the Steklov and the Robin problem, and in particular, just by using the fact that this problem has a positive spectrum of infinitely many eigenvalues of finite multiplicity, tells you that in the case of the Robin problem, for any k, lambda k is going to be negative when beta, the Robin parameter, goes negative. So I guess this is enough for what concerns the Laplacian. So let's go finally into Bilaplacian problems. So just to recall you, for those of you who don't know, the Dirichlet problem for the Bilaplacian is this problem here, where the equation now in omega is not anymore a second order, but it's fourth order, so it's the Laplacian of the Laplacian. So it's fourth order derivatives equal lambda u. And now for the Dirichlet problem, for any problem, we have to set two boundary conditions, and the Dirichlet problem is given by u and the normal derivative equals 0 at the boundary. So one thing that I forgot to mention is that here in our analysis, omega will be a domain in Rd, d is the dimension, and always with at least Lipschitz boundary. So like for instance, this problem is well set if omega is just of finite measure in Rd, but since for the Robin problems, we will consider also boundary terms like this where traces are involved. We need at least Lipschitz. Otherwise, we would need to state problems in a very weak formulation, and we do not want to go into those type of details. So this is the Dirichlet problem for the Bilaplacian. Actually, we are considering a generalized version of this, which is this type of problem where you have the appearances of lower order terms of this type. And this problem is interesting because the Bilaplacian is actually a model for plates. So like in this case, you have a vibrating plate which is clamped. If you, instead of lambda u, you write f, you have the load of a plate. In this case, with this minus alpha delta u, the plate is actually under stress. So you may have a plate under tension or under compression. These are the two cases. And I just want to mention it. This problem is strictly related with the buckling problem, which is an eigenvalue problem for an operator pencil. So it is a problem which is of quite important interest. And this is the problem essentially still for a clamped plate. So this is a problem set in H2 0, because now the energy space is H2. So the Neumann problem, instead, where the plate is completely free, is this very ugly looping problem, where you still have two boundary conditions. One is now of second order, and the other one is of third order. Here we retain the stress parameter alpha, and you see that also there is the appearance of a new parameter sigma. And this sigma is what is known as the Poisson ratio. This is a quantity which is related with the stiffness of the material. So it's not a structural thing, it's really about the material that it's used. Also this coefficient sigma may be a function in general, but we will, for simplicity, consider just constants. And the range of sigma is this one. So we will avoid the extremes, because nested problems may come out. So we will consider just sigma, a constant within this range. And for the rest of my talk, we will not consider what happens when sigma varies. We just fix sigma and consider variation with respect to the other numbers. So now I don't want to comment on the fact that these boundary conditions for the Neumann problem are very ugly, and usually one tends to avoid them by writing the weak formulation and dealing with it. But anyway, this is enough for us to finally state what is for us the Bilaplacian with Robin boundary conditions. And as you may expect, it's just an interpolation between Neumann boundary conditions and Dirichlet boundary conditions. Now, of course, since we have two boundary conditions, we will interpolate separately, in the sense that we will have two different constants and not anymore one, as for the Laplacian. And at the first glance, it may seem like a little pretentious as a problem, but if you write down the quadratic form, you really see that there is some sense behind this. So this is the quadratic form associated with this Robin problem. So you see that here you have the second order, the leading terms, where you have the appearance of the Hessian and of the Laplacian, and here you have the sigma parameter, the Poisson ratio. Then you have the tension, the stress perturbation here. And finally, you have these two boundary terms. The one in beta is a term concerning normal traces, while the one in gamma is just say the usual traces of the function. And speaking of plates, this is, of course, as you may imagine, a good model for representing plates which are not clamped or free, but which are elastically supported. Now, gamma will be a coefficient, the elastic coefficient of the horizontal elastic response, while beta is the transversal one.
Davide, I will stop you for a second. There's a question in chat from Konstantin Pankashkin who asks whether the delta in the boundary condition is the usual Laplacian in the domain or the Laplace-Beltrami operator on the boundary.
No, this is the Laplacian, say this is the trace of the Laplacian. Mm-hmm. This is not the Laplace-Beltrami operator, this is the full Laplacian. So this, like this delta u will be the second normal derivative plus the curvature times the normal derivative plus the Laplace filtering.
Okay, all right.
Of course, these boundary conditions do not make any sense if you consider weak solutions, because weak solutions will be in H2 and you cannot trace second derivatives. But if your solution is in H4, which is then the strong solution, you can trace the Laplacian. You can also trace this nasty third order operator, and everything makes sense.
All right, thanks.
So, okay, we were saying about this quadratic form. Actually, for this Robin problem is set in H2. If you set this quadratic form in H2 0, you end up with this Dirichlet problem, as you expect. Now, for those of you who have quite some experience with the Bilaplacian, you will know that you have the possibility of fixing two traces, of fixes no traces, and also fix just one trace. So what happens if instead of taking H2, you take H2 intersection H10, meaning that you just fix U, the solution, to be 0 at the boundary? Well, in this case, you end up with this intermediate Robin problem that we call Navier-Robin. Why we call it so? Because if you set beta equal to 0, this is the classical Navier problem for the Laplacian, which is for the Bilaplacian, sorry, which is used for modeling plates which are just hinged and not clamped. Similarly, if you set here the normal derivative to be equal to 0 and the other trace to be free at the boundary, you end up with this other intermediate Robin problem, which we call Cutler-Sigillito, because it was somehow introduced by Cutler and Sigillito in a paper dated 1968. They studied actually a very closely related problem, which was of Steklov type, where this here the equation is 0. You have this equation equals 0, and this gamma here becomes the spectral parameter. So similarly, also this Navier problem, this Navier-Robin problem, is related with what is known as the classical, some sort of classical Steklov Bilaplacian, where you have 0 here in the equation, and here you have the eigenvalue.
I will stop you once again for a second, Davide. I think this will clarify something. So Dima Vasiliev says he has a question regarding the sign of the Poisson ratio. I mean, I'll let him ask his question, I guess.
Well, thank you. Hi. Could you go a couple of slides back when you to the place where you introduced the Poisson's ratio?
Here.
So you see the formula sigma belongs to this interval. Usually it's the other way around. It's between -1 and +1/2. Do you see?
Yeah. Okay. Yeah. This is because usually it's you think of this ratio in 2 dimensions. So the full range would be -1, 1. It's, say, for ordinary material, how to say, when say the negative Poisson ratio means that the material is non-Newtonian, while usual materials have a Poisson ratio between 0 and 1/2. This is the reason. Actually, this is the full range mathematically, because if you look at the quadratic form, here it's where it appears. So the part with the Hessian is coercive, poses no problem at all. If you say this is the Frobenius product, so this is the product of di dju, di djd. So you multiply analogous derivatives, and therefore the square u becomes just the sum of the squares of the Hessians. So this is the good part.
Basic idea. I see that you are working in a more general setting, in an arbitrary dimension. So for me, plate theory is when you start in dimension 3 with not with plates, but with linear elasticity, and you define Poisson's ratio in dimension 3, and it has to be between -1 and +1/2, so the opposite of what you wrote. And after that, you develop a plate theory. So maybe, okay, just something for you to check, but that's the way it's normally done in mechanics. You start in dimension 3, and in dimension 3, Poisson ratio is between -1 and +1/2, which is the opposite of what you wrote. And then you develop a plate theory in dimension 2. So I'm just pointing out that the usual Poisson ratio for simple people, you know, in dimension 3, is the opposite of what you wrote. Just check it afterwards, whether you have agreement with sort of normal conventions used in plate theory.
Okay, I will check it. Okay, thank you very much for your remark. But yes, anyway, if you just consider this sigma as a coefficient here, it makes sense to consider sigma in this range, because this is what makes the form coercive. This is essentially the good term. So when sigma is 0, you just have this term. When sigma is non-zero, you have to add this term with the Laplacians, which is non-coercive. And indeed, when sigma is equal to 1, you can get into troubles. For sigma in that range, this is well-defined and coercive, and has all the properties that one would like to have. So, yes, to go back here, so you have these two intermediate problems, which are related with the already known Steklov type problems for the Bilaplacian. And now I want to give you some, say, some interesting appearance of a problem of this type in the theory of traces of Sobolev spaces. So if you take the traces of an H2 function, you get the trace of the function and the trace of the normal derivative. And it's relatively easy to prove that this graph is a subset of this space, is at least contained in this space, where you have to properly define H3/2 and H1/2. And this is true for omega Lipschitz domain. So if omega is smooth enough, then you have the total trace theorem that says that you actually have complete decoupling of the two. So the traces of H2 functions cover completely the space. If, however, omega is only Lipschitz and not much more, then the inclusion can be proved to be strict. There are actually counterexamples, and the full space of traces can be actually characterized using eigenfunctions of this type of Steklov problems, where now you fix one as a parameter and the other as an eigenvalue, and vice versa. And using eigenfunctions of these type of problems, you can completely characterize the space of traces for H2 function. So this is just to give you an idea that this problem does not come out of nothing. There are interesting relations with other problems also, not just because it's nice. So let me state some interesting facts, some basic facts about this problem before going on. So we are going to fix this sigma in the range that we said. Now, the Navier-Robin problem can actually be associated with the case gamma equal +infinity. Why is that? Well, if you go back here, you see that since gamma appears here, if you let gamma go to +infinity, somehow remembering what happens for the Robin Laplacian, you see that at the limit, you should have u equal to 0, meaning that you should recover this Navier-Robin problem. And so we associate the Navier-Robin problem with the case gamma equal +infinity. In a totally similar way, we associate the Kutrus-Giglito problem with the case beta equal +infinity. And as you may imagine, the Dirichlet problem is associated with the case beta equal gamma equal +infinity. Now, interestingly, for any alpha in R and for any beta in R or equal to +infinity, the bilinear form Q is symmetric and into elliptic, as essentially one would like to have. The operator and the resolvents are actually continuous with respect to the triple, alpha, beta, gamma in R. And we also have the min-max characterization of the eigenvalues. Of course, when beta and or gamma are equal to plus infinity, the space has to be changed accordingly, but the characterization is as you may expect. And also the eigenvalues lambda k are piecewise analytic with respect to the triple alpha, beta, and gamma. So essentially, this is to say that the problem that we stated is regular enough, is nice enough, so that now we go into analyzing say deeper properties of the problem. And in particular, what we have in mind is analyzing the asymptotics when the parameters go to plus infinity or minus infinity. So let's start with a case where we send the parameters to plus infinity. We first of all consider just the Robin parameters, beta and gamma, and then we will see that the tension parameter is actually of a different kind. So for any k, the lambda k is monotonically increasing with respect to both beta and gamma, as you may expect. When you send gamma to plus infinity, the eigenvalues converge to the eigenvalue of the Navier-Robin problem, which is what you expected, and you have also convergence of the eigenfunctions weakly in H2. When you send beta to plus infinity, you have a convergence to the Cutrer-Sigillito eigenvalues and also convergence of the eigenfunctions weakly in H2. And finally, when both beta and gamma go to plus infinity at the same time, you have convergence of the eigenfunctions and of the eigenvalues to those of the Dirichlet-Bilaplacian. Now, here, these statements are valid for beta and gamma in R union plus infinity, meaning that here, if you set right from the start beta equal plus infinity, you're starting with the Cutrer-Sigillito problem, and you're sending gamma to plus infinity, meaning that you recover the Dirichlet problem at the limit. And similarly, here you do the reverse. If you set gamma equal to plus infinity, you have the Navier-Robin problem, and you get convergence to the Dirichlet problem. What does this mean? That if you start with just the full Robin, where you have beta and gamma in R, you can go, either you can go directly to the Dirichlet, or you can go first to the Navier-Robin and then to the Dirichlet, or you can go through the Cutrer-Sigillito and then to the Dirichlet. Meaning that everything essentially works in the nice way, as we would expect. And in particular, if we have more regularity of the boundary, we say that the boundary is C4, then we have we can prove also convergence of the corresponding resolvents, meaning that we have also this rate. We do not think that this rate is optimal, but this was, let's say, a first attempt. This is when gamma goes to plus infinity for finite beta, and this is when beta goes to plus infinity for finite gamma. Meaning that this is, say, the equivalent for the first case in the previous theorem, and this is the equivalent for the second case for the third theorem. We expect to have an equivalent also in the case both beta and gamma go to plus infinity simultaneously. The thing is that in order to have that, we would need better estimates on the coefficient of regularity estimates for say the B-harmonic equation. We expect this to be true. It's just that checking it is not really an easy task. It's quite complicated, requires very deep knowledge of regularity theory, and we didn't do it, but we definitely expect it to hold. So, as we said, this is what happens when Robin parameter go to plus infinity. Now, the thing is that Robin parameter are say, in a sense, effective on the boundary, while instead the tension parameter alpha happens to work in the interior, so it seems to be really much stronger. And indeed, this is what we see when we set the tension parameter to go to plus infinity. So if you give a look back at the equation, when you let alpha goes to plus infinity, essentially you expect this problem to converge to a Laplacian problem of some kind. Because say you divide by alpha, you see that this goes to 0, and this lambda over alpha will go somewhere. And this is indeed the case, and we can prove it, that when you say alpha going to plus infinity, now you renormalize the eigenvalue lambda k divided by alpha, and if we take either the Navier-Robin problem or the Dirichlet problem, meaning that in both cases you have u already 0 at the boundary, then at the limit you recover this mu kd, which is the kth eigenvalue of the Dirichlet Laplacian. And you have also convergence of the corresponding eigenprojection, so it's not just by chance. If on the other case you consider the full Robin or the Kutre-Sigillito problem, the same stuff converges to the Neumann problem, because here you don't set u0 at the boundary, so essentially you are converging to the Neumann problem, and with the convergence also of the corresponding eigenprojections. So why does this happen? Well, essentially the terms in alpha going to plus infinity kills everything else in the quadratic form. Also the Robin parameters. So in this case, you see that beta and gamma are fixed. So what happens if you allow them to vary? So let's say that you keep fixed beta, but now you allow gamma to go to plus infinity as alpha, and precisely we say gamma equal alpha gamma tilde, where gamma tilde is a constant in R. Then in this case, that boundary term is not killed anymore, and you have convergence to Robin eigenvalues with the Robin parameter gamma tilde now, which is precisely what you expect. Now, the interesting thing is that is what happens if instead of letting gamma go to plus infinity, we let beta go to plus infinity. So let me just go back to the statement of the quadratic form, which is here. So you see that now, if you divide by alpha, this is going to 0, this is going to 0 because gamma is fixed, and this is not going to 0. Now, there is a problem though, because at the limit, we are falling into H1, an H1 space. And say the normal derivative of an H1 function is not well defined in general, unless of course the function is not only H1. So in that case, you see, when you now fix beta, gamma, and you let beta go to plus infinity in this way, you have convergence again to some sort of eigenvalues, and these eigenvalues are eigenvalues of a very strange problem that apparently was never studied before, where you have essentially you have this term, which is a proper Laplacian, plus a boundary term. And this boundary term is defined in this way. So the space is a space of the type H1 times L2 of the boundary, where these two functions, U and F, can be reached by approximation of H2 function simultaneously, meaning that U has to be an H1 limit of an H2 sequence, and the term F in the boundary has to be the limit of the same sequence with respect to say it's the limit of the normal derivatives at the boundary of the same sequence. So this space is very strange, also because if omega is not smooth enough, this space is going to be a strict subset of H1 times L2 of the boundary. And the properties up to now are not very clear to us. Just to say that in this case, we have to restrict to the case beta tilde, sorry, strictly positive, because if beta tilde is negative, it seems that this problem is not, say, does not have an increasing sequence of eigenvalue going to plus infinity. So it's not clear yet what happens in this case. So this is essentially everything I wanted to tell you in the plus infinity regime. So now let's go to the minus infinity regime, where divergence is expected to happen. And indeed, this is the case. So in this case, we treat alpha, beta, and gamma simultaneously, because in all of them, we will see divergence. So we start with the case of alpha going to minus infinity. And here, let me recall that omega is only Lipschitz. So we have an upper estimate on the rate of the divergence, and you see that the divergence when alpha goes to minus infinity of the, say, of the first eigenvalue is at most as minus alpha squared. If instead you let beta go to minus infinity, now the divergence rate is at most minus beta squared. And finally, when you let gamma go to minus infinity, you have this divergence rate, which is at most minus gamma to the 4/3. So at first we were quite, we were thinking that this was sort of bizarre, but indeed, if you do the computations, you see that this is what you have to have as rate of divergence for these cases. So this is true for omega, just Lipschitz, and for any case, beta and gamma equal to plus infinity in case. So, for instance, in this case, for alpha, this is true both for the full Coban, the Cutre-Sigillito, the Navier Coban, and also for the Dirichlet problem. So actually, sorry, actually in the Dirichlet case, so if you consider eigenvalues of the Dirichlet Bilaplacian, we know, because we proved it in a paper with Pedro Freitas and Pedro Antunes, that this is the rate of convergence, and we actually computed also the coefficient. So this is going to be important. Well, is that the other cases, of course, are completely new. So if we increase a little the regularity of the boundary, so we consider C1 domains instead of Lipschitz, we have a better understanding, and we see that in this case we have also an estimate from below of the rate of divergence. So we see that indeed when alpha goes to minus infinity, the eigenvalues diverge as minus alpha squared. When beta goes to minus infinity, they diverge as minus beta to the 4th. And when gamma goes to minus infinity, they diverge as minus gamma to the 4/3. And this is essentially the summary. Now, of course, these are just estimates, and we do not have the precise constants in front of them, even though we expect that the constants are going to be the ones that we found here. Now, one thing that that is important to say is that when beta and or gamma are equal to plus infinity, these estimates are not available yet, in the sense that this last theorem is true only for the full Coban in H2, where beta and gamma are in R. Why is that? Well, because this, this result is obtained using test functions. So we devise test functions based on exponential type functions, and if you're in H2, you are completely free to choose the test functions you want, because you do not have any constraint on the boundary. But when beta is plus infinity, for instance, you are forced to take test functions which have normal derivative equals 0. When gamma is equal to plus infinity, you must take functions which are 0 at the boundary. So you have to use completely different test functions, and apparently this does not seem to be the right technique to use in that case. However, we strongly suspect that these are the rate of divergence, and probably with the same constant. And actually this is given, the suspicion, say, is given by the previous theorem, which is available in all cases, because this is given, this is obtained through estimating the quadratic form. And in particular, we know that for the Dirichlet problem, this is the rate of divergence with the coefficient precisely 1/4. So this is precisely this that we said. So we expect this behavior to hold in any case. And finally, we covered in these theorems the situation where we let just one parameter go to plus infinity or minus infinity, while the other are more or less bounded or fixed or anyway controllable. So what happens if we leave, we let everything go random? Well, the situation is quite complicated, and we haven't studied it deeply enough. But one question that we were thinking about is if it is possible to fine-tune the parameters so that just a finite number of eigenvalues become negative and not all the spectrum go negative. This is, for instance, this may be achieved by letting alpha go to plus infinity while beta and or gamma go to minus infinity in some way. Anyway, this was just, say, a first study in the asymptotic behavior at plus and minus infinity, and deeper studies are required in this sense. So, in the last 5 minutes, say, I would like to briefly cover what happens for shape perturbation. So, as we said, for the Robin Laplacian, we have some results regarding shape optimization, like Faber-Cran type inequalities, counterexamples when the Robin parameter is negative, and so on. So here we want to analyze what happens if, instead of moving the parameters, the Robin parameters or the tension parameters, we move the domain omega, which is the shape. So we fix a reference domain omega, which is Lipschitz, and we consider diffeomorphic domains phi of omega. So the technique will be to set the problem on phi of omega, pull it back to omega, and then consider the operator as dependent on phi, and then differentiate with respect to the phi, which is now belonging to a linear space. So as a notation, we set lambda k of phi to be the kth eigenvalue on phi of omega. And then we have this nice theorem which says that if we end up in a domain of class C4, then you take a simple eigenvalue on that domain, then the Hadamard derivative is of this form. So you have the integral on the boundary of some function concerning the eigenspace, the eigenfunction v, which is L2 normalized now. Then the rest is essentially the classical term that you have in Hadamard derivatives. So now this function g here for the full Robin problem is very nasty looking. However, I mean, you see that this term comes from the Hessian term, this term comes from the Laplacian, this from the tension, and the rest comes from the other boundary terms. So this is the formula for the full Robin problem. For the Navier, Robin, the Coutras-Sigillito, and the Dirichlet problem, you have analogous formulas, analogous G functions that I'm not going to state for the sake of simplicity. Now, of course, this is for simple eigenvalue. In the case of a multiple eigenvalue, you know that in general you cannot differentiate. You may have splitting, and this is bad for differentiation. However, if you consider elementary symmetric functions of the multiple eigenvalue, you can actually show that these functions are now, they overcome the splitting phenomena, so they become analytic, and you can actually differentiate, and you get a formula which is completely analogous of this. And I do not want to state it because it's a little more complicated, but it's completely analogous. So now, as we mentioned shape optimization problem, we have the derivatives of the eigenvalues with respect to the shape. So it makes sense to use the Lagrange multiplier theorem to have some result on criticality for eigenvalues. So we fix now phi of omega, phi tilde of omega to be plus C4. We consider an eigenvalue of multiplicity m, so m is generic. You consider an L2 orthonormal basis of eigenfunctions, and then we get a complete characterization of critical domains. So phi tilde of omega is critical if and only if this quantity here is constant on the boundary. So this quantity is just that functions g that I showed you 1 minute ago, computed on every eigenfunction of the base, and then you sum. And if this quantity is constant on the boundary, then you know that this domain is critical with respect to volume constraint. So if you fix the volume. And in a totally similar manner, the same is true if instead of volume constraint you take perimeter constraint, only that now instead of having this quantity constant on the boundary, this quantity has to be a multiple of the mean curvature of omega, of 5 tilde of omega. So now with this complete characterization, the natural question to ask is what happens for balls? Because we know that balls are in very interesting domains when considering shape optimization and shape perturbation. For this problem, we have lots and lots of Faber-Cahn type inequalities for the Laplacian. We have some Faber-Cahn type inequality for the Bilaplacian, because the Bilaplacian case is much more complicated. So what happens if we take balls? So in the case of balls, the interesting thing is that this quantity here can be shown to be always radial. So if you take this quantity just inside the ball, it turns out to be radial. So in particular, it's constant on the boundary. So you see that this means essentially as a corollary, sort of a corollary, that balls are a critical point for any eigenvalue given under volume constraint, and in particular, since the curvature at the boundary of the ball is constant, balls are critical also under perimeter constraint. Of course, this does not answer the question of shape optimization, say, is lambda 1 maximized or minimized by the ball under perimeter or volume constraint? And I would like to remark that this problem is very difficult. It has been solved just in very limited number of cases. For instance, the Dirichlet, for the Dirichlet problem, it's still an open problem. It's known as Rayleigh conjecture. It's been proved in dimension 2 and 3, but the general case is open. For Neumann problem, it has been proved by Mark Chasman relatively recently, actually. But we didn't even try to do it for this new Vauban type problem, because I mean, essentially there are no techniques available in this case. So this is an open problem that is going to be probably very difficult. So I think that this is the right place to stop. So thank you for your attention.
Thank you for the presentation, Davide. It's now time for questions. So does anybody have one? You can write them in chat or unmute yourself and ask the question. All right, I'll start the ball. I mean, it might be quite a simple question, but when you define the full Robin problem, I mean, you matched your boundary conditions in a specific way. Is there a reason why? Like, would it have worked if you had matched the boundary conditions, say, with inverting the right-hand sides, for example?
Yes and no, in the sense that if you are completely free to invert, say that you set this part equal to minus gamma u and this part equal to minus beta du the nu. The thing is that in that case, the quadratic form has to change dramatically, in the sense that this is the natural quadratic form that you would put adding boundary terms of Robin type. And essentially, say, when you want to derive the strong formulation, so you start integrating by parts these integrals here, you see that these terms appear precisely in correspondence of normal derivatives. So you will have this whole stuff multiplied by the normal derivative of v, if you integrate, downloading all the derivatives on u, and sorry, this term will be multiplied by by just v. This term will be multiplied by the normal derivative of v. So in a sense, this is the natural problem. Of course, you're completely free to invert them, to write a different quadratic form. This seemed quite natural also because, as we said, if you just say beta equals 0 and you let gamma to be the eigenvalue, then this becomes a well-known Steklov type problem for the Bilaplacian, and this is the one that Luigi Provenzano and myself introduced, which can be seen, for instance, if you take the Neumann problem and you put a weight that is now concentrated on the boundary, you end up with this type of problem. So in a sense, these are the natural terms to add to get a Roman type problem. But I mean, any other thing would do.
All right, thanks. It's quite clear. Are there any
can
questions?
I ask a question?
Mm-hmm.
You absolutely can.
Oh, yes, I'm Alice Chen. Thank you for the talk. Let me ask an outside question. That is, are there any results in this Bilaplacian operator eigenvalue dimension sensitive? That is there difference? I'm particularly interested when dimension equal to 3 or 4. Is it different than other dimensions?
Yes, indeed. So usually, like in this type of results of studies, the different dimension does not really come up, so you don't see it. I know, I'm not an expert, I haven't studied it, but I know that for some type of estimates for the Bilaplacian, for the Neumann Bilaplacian, actually the dimension makes a lot of difference. So you have dimension 2 is a case, dimension 3 is another case, and then you have dimension 4 and bigger. So you have some sort of a difference between dimension 2 and 3 and 4. This happens, for instance, also for the, say, the Faber-Krahn inequality, which says that the ball minimizes the first eigenvalue. Now, the proof that we have works only for dimension 2 and 3, and that argument does not work at all for higher dimension. So, in a sense, sometimes you don't see the difference. Some other times you really see a difference between lower dimension, and by lower I mean 2 and 3, and higher dimension. So I know that there are some results in this sense, but I'm not an expert.
So, thank you.
All right, thank you very much for the question. So the next question comes from the chat from Rick Lugeson, where he asks, in the quadratic form, would it make sense in the boundary term to use a dot product of the gradients rather than the product of the normal derivatives? And he apologizes if it was covered earlier.
No, it was not covered. So, okay, actually, when I first was thinking about this problem, I was thinking of a problem where here instead of normal derivative, you have gradient. What happens is that essentially, in that case, the couple, the normal part and the tangential part, so you would end up with a problem where here you have the normal derivative, and here you would have this plus a term of the type Laplace-Beltrami at the boundary of U. So in that case, linking with a question from before, in that case you would have the appearance of the Laplace-Beltrami operator of U here on this side. But okay, this is a personal opinion. I'm not sure how interesting that would be, because that would add just a term here. I was thinking of it also last week. It may be interesting, but I'm not sure how much interesting it is. But it definitely, I mean, I didn't do any computation at all. So it could be that I'm just wrong and very interesting results come out.
All right, thanks for this. Let's hope it answers Rick's question. Are there any other questions or comments for Davide? Well, I'll have a last one myself, which I guess is bit more of oh no, I mean, there's an answer from Rick here. He says that the interest probably depends on whether there's a good physical interpretation of that boundary energy term.
Yes, I'm not sure. I have to say I'm not an expert of mechanics of solid. I know just something, some little things that, for instance, led me me and James Kennedy to state this problem. It may have some interest actually, because one may decompose the elastic force into transversal, longitudinal, and tangential parts. From an engineering point of view, it could make a lot of sense. Say that mathematically, it seems to me, this is just a feeling though, it's not, I'm not sure about that. It seems to me that this is the most relevant problem because, for instance, as I told you, this problem is also related with the problem of traces of H2 functions, where you have a problem of this type coming out. So you see that in this case, you have a problem which is precisely like this.
Okay, we have another question in the chat where Muhammadun Gum wants to ask what is the regularity of omega in the Robin Bilaplacian problem that you have.
Okay, so in general, the regularity we require is Lipschitz, because this is what makes this quadratic form well defined. I know that there are modern formulation of Robin problems which require less than Lipschitz, but this is a whole different story. For some results, we need a little more regularity. For instance, let's say this convergence type is true for Lipschitz, while in this case we require C4. Other cases we require C1. Sometimes we may require C2. This depends mainly on the technique that is needed in order to prove different results. But say the basic regularity is Lipschitz. Below Lipschitz is essentially you change the problem.
All right. I had a last question myself. So when you had that say that weird problem where you converge to the eigenvalue to some problem on the inside and on the boundary, I just wanted to mention that this looks very similar to a say Neumann version of a dynamical eigenvalue problem that you'll find from von Bello and François. So it's not exactly the problem that you ended up having, but I think that if you want to find literature around that problem and similar problems where you have these pairs of functions inside and on the boundary, looking around that paper would be
okay.
I mean, there's maybe one paper from
yes. Could you send me the reference, because I actually this problem was one of the last thing we did, and we were surprised that it seems quite complicated. So we said, okay, for the moment we write the paper and then we will see.
Yeah, I mean, I actually had to use that problem, a similar problem once, and I found one paper about it. But maybe I mean, one could look a bit more.
Yeah.
All right. So, are there any other questions for Davide? Well, not seeing any of them. Thanks again for speaking.